Hi everyone, this is Sangeeta Ghangam, and I'm here to present the work that we did as part of the third DIHARD challenge as part of the Diaboliic team. And with me today is my teammate, and I'll also let him do a quick intro.
Hi everyone, this is Wenda Chen. We are teammates for the Diaboliic team for DIHARD 3 challenge. We are here to present the preliminary version of our system.
Thank you, Wenda. So we'll start quickly with our team structure, as well as a quick summary of the approach that we took. So our team had people from many different places. So we had a team from Lyon, as well as from IRIT, both from France, and then Wenda and myself. And in summary, we had many ideas in the team, almost as many as the total number of team members, but we kind of zeroed in on the following three areas. So we looked at the approach taken for segmentation, embedding, as well as for resegmentation at the end of the pipeline. And we focused on this as three separate systems or three separate efforts, since the team is not based at the same location. And then at the end, we used an ensemble approach to combine the each system end result into a single per track result that we then went ahead and uploaded. To get started with, we will quickly add some details about the approach that the team took for segmentation. The baseline pipeline that's used as part of this particular module is based on PyNode. And for those of you who may not be aware of PyNode, essentially PyNode creates a modular approach to doing speaker diarization, where each one of the modules can be addressed as a sequence labeling task, such that the input is essentially a sequence of feature vectors, and the output is a sequence of labels, where the different type of labels actually depend on the number of classes that's applicable for that one module. And there is also a code available as part of the PyNode pipeline to train your own neural network. So the PyNode pipeline was utilized here as a starting point. And then one of our team members made changes to this particular pipeline to comprehend not a sliding window type of an audio input signal, but actually using audio segments. And the approach of using audio segments is what we found out as we ran through the different test scenarios and training was actually did provide a lot of improvement in the end result versus using a sliding window anywhere from 0.5 to about 4 seconds or so. So that is the improvement, which, as mentioned here on the slide, it definitely improved the overlapped speech detection aspect. The multitask training approach certainly helped with being able to train this on the Voxella dataset, which was key to ensure that when we ran it through the DIHARD development data, we saw good results. Now I'll pass it on to my colleague, Wenda, to talk more about the embedding approach.
Yep. Thanks, Sangeeta. So here, after we have a reasonable pre-segmentation based on the VAD speaker change and overlap detection, we want to produce the efficient embedding for those speech segments in order to support a better resegmentation at a later stage. So we used the X-vector-based speaker identification model as our initial baseline model. This X-vector structure, as shown on the right figure, use attentive pooling and TDNN networks to learn using the target speaker label by producing the speaker embedding at 256 dimensional. The learning was through additive margin softmax loss. And this pre-training was done on VoxLab database. And then from VoxLab to test, we used the voices database to see which model was better for the short duration segments. So we can see in this table, there we select, there's two models that perform very well for different lengths of segments. The first model performed extremely good for 1 second and 2 second type of cases. And the second model performed better for 4 seconds all the way to the full speech length. So here we are evaluating by equal error rates. So we also further test these models on the DIHARD 3 development data and evaluated the average distance of all the embeddings from the same speaker. We found that the model 1 has lower distance, cosine distance, of all the embeddings that belong to the same speaker. So this is quite expected because we observed that in the segmentation data sets, the average length of the segments are slightly less than 2 seconds. So we tested these two model on the development data of the DIHARD 3, and which evolved from the VoxLab and Voices, so which make it usable from speaker ID embedding to diarization purpose. Thanks.
Thank you, Wenda. And now we'll move on to the next approach that we used, which was the resegmentation. So for this particular system, what we did was we used the baseline Pioneer system. This was based on the second DIHARD submission that was done 2 years ago. And then the Pioneer embeddings actually were utilized as the input into this particular system. And in this case, the embeddings were trained on a sliding window with up to a 4-second duration. And that particular flexibility in how those embeddings were created was essential, because one of the key steps as part of this particular system approach was to kind of transfer or translate that particular embedding results into speech segments that can be utilized in the Kaldi ARC format. The resegmentation system was reused from the VBX, which was actually the part of the second DIHARD submission as well. That particular system utilizes a Bayesian hidden marker model where states correspond to the speakers and the transitions correspond to the actual speaker turns. Since it uses an I vector-like model and then converts each of the speakers as well as the segments into a Gaussian mixture model type of a representation, it does a really good job at robustly identifying for a given set of embeddings what is the connection between a speaker as well as the speaker segment. So once the speech segments were actually converted into the Kaldi ARC format, we used that as the input to process that through the VBX resegmentation system. So in this case, the entire VBX resegmentation part of the pipeline was reused as is. There were a few key changes that were done in order to optimize the end result. The p-loop parameter, which helps identify the number of speakers for a given set of data, that was optimized to a certain number based on a few runs through the third DIHARD development dataset. Also, the interpolation alpha value, which in the end was influencing the PLDA result, was actually fine-tuned to 0.75, which is different than what was captured in the baseline. So these different variables allowed us to fine-tune the resegmentation approach, which could then be easily used and integrated with the Pioneer embeddings. A 4% improvement in the word error rate was seen. So previously we were seeing an end error rate of about 28, and then with the use of the resegmentation approach, it went down all the way up to 24. So even when utilized with pre-existing systems, combined with that resegmentation approach, there was definitely an improvement in the end result or the error rate that we noticed at the end. So now I would like to summarize the different systems that we did submit to both track 1 as well as track 2. The track 1 system was a combination of pipelines that utilized the voice activity detection result through the Pioneer baseline pipeline, which was submitted to the second DIHARD competition. We also utilized the third DIHARD system baseline and did an ensemble of both of them to actually provide the end result, which we submitted to track 1. And this particular ensemble was created using the overlap technique. For track 2, we actually combined 3 different systems. One was the Pioneer Fusion, which combined the 2 approaches that you just heard about from both the segmentation as well as the embeddings. This particular Pioneer pipeline was then combined with the second system, which had the resegmentation output, and then another baseline system, and in this case, the VBX baseline system, which is an updated system, was utilized. All 3 of these systems were combined using the Dover algorithm. So we used 2 slightly different ensembling techniques for both track 1 and track 2. And I believe based on the leaderboard results, we were placed on number 6 for track 2. I think this page summarizes some of the references that we utilized. I think I would like to say the third DIHARD competition gave me a good opportunity to understand how the different innovations in the speaker identification area can be brought out in the text-independent diarization area, which was a key learning for me. Also, some of the new ensembling techniques and how effective they are were very evident to me once I saw the output from the different combined systems. I would now like to pass it back on to Venda and see if he has any takeaways from the competition.
Yeah, this competition is teach us a lot on how we extend the speaker identification embeddings to the application of diarization. And also, we, as a joint team with Lium and IRT, we managed to work together on combining the systems and produce better results. I'm very thankful for the organizer for this challenge.
Thank you, Venda. Likewise, I would also like to thank our entire Diaboliic team, almost a cross-site, cross-geo team, who came together to put together these different systems and the final submissions that went into both the tracks. I would also like to thank the third DIHARD Challenge organizers who worked very hard to ensure that the entire systems, the scoring servers, etc., ran to the very last submission point, which did give us some more time to try out additional things that we wanted to. So thanks to the team and to the organizers and for this opportunity to present today. Thank you.
Thank you.